Software engineering functions as the structural management of complexity and scale. Much like a suspension bridge designed to flex under load, a software system must be engineered to handle shifting data volumes without a failure of its underlying logic. Building a standalone script involves basic logic, but engineering a system for millions of users requires a robust architecture capable of sustaining constant operational stress. To see this in practice, consider a smart parking management system for a multi-story shopping mall. This project requires automated space allocation, digital payment processing, and integrated security monitoring. A system of this scale involves high-stakes variables. It must interface with physical barrier hardware, process financial transactions in real time, and manage high-volume traffic patterns without delay. Before any code is generated, the team must establish a foundation through requirement engineering, defining the exact problems the software is intended to solve. These requirements act as a safeguard against complexity. They ensure the final product remains a coherent system, rather than a collection of uncoordinated features. Requirements are categorized into two types. Functional requirements are statements of specific services or functions the system must provide to the end user. For our parking system, functional requirements include the ability for a driver to reserve a spot via a mobile app and the implementation of automatic license plate recognition at entry points. Non-functional requirements define system properties and constraints. These focus on broad attributes like performance, security, and reliability. The mall system carries specific non-functional constraints. It must maintain 99.9. These constraints are often the most critical. If the system fails to meet its uptime requirement, the functional features, like spot reservation, become inaccessible, rendering the software useless to the customer. Functional requirements define the specific features of the software, while non-functional requirements dictate the performance of the system as a whole. Translating human-readable requirements into a technical blueprint is a primary engineering challenge. Engineers use UML class diagrams as the structural blueprint for object-oriented systems. Nouns like driver or payment become classes, with data attributes defined at the top. Verbs like reserve or pay become methods at the bottom, defining the specific actions those classes perform. This modeling phase ensures that the entire development team is building from a shared, documented logic before the first line of code is written. Once the blueprints are set, the project manager must choose a process model to organize the team's labor. The waterfall model flows linearly from requirement analysis through testing. It is effective for stable, well-defined requirements. But without a feedback path, steps don't overlap. Mid-project changes are difficult, and major errors may go undetected until the final review. The V model addresses these risks, extending the waterfall approach with a heavy emphasis on quality assurance. It creates a horizontal mapping between each development phase and a corresponding testing phase. This ensures that testing is planned long before the code is actually written. This model forces a distinction between verification, asking if we are building the product in the right way, and validation, which asks if we are building the right product for the client's needs. While these models provide discipline, they are often too rigid for the fast-paced, shifting requirements found in modern software development. To provide value more quickly, engineers move toward delivering software in functional slices rather than as a single final release. The incremental process model delivers software in staggered sequences. The first increment delivers a core product for immediate use. Subsequent increments add new features based on priorities, allowing the product to grow and adapt over time. This incremental approach reduces the risk of project failure by integrating customer feedback into each stage of development. Agile methodology takes this further, using an iterative process to accommodate constant change. Scrum is the most common method. It organizes development into time-boxed iterations of 1 to 4 weeks called sprints, each resulting in a demonstrated software increment. The Scrum framework relies on specific roles: the product owner, who defines the features, the Scrum Master, who facilitates the process, and a self-organizing team that executes the work. Coordination is maintained through the daily Scrum meeting. In just 15 minutes, team members answer what they did yesterday, what they will do today, and what obstacles are in their way. Extreme Programming, or XP, is an agile framework that focuses on technical practices such as pair programming and test-first development to ensure high code quality. In pair programming, 2 people code at a single workstation. This real-time review identifies errors as they are made, facilitating knowledge sharing across the team. XP also emphasizes refactoring, modifying and optimizing existing code to improve its internal structure without changing its external behavior. By shortening feedback loops and empowering small teams, Agile frameworks allow developers to remain maneuverable in the face of unpredictable requirements. An Agile process is only effective if the underlying code is flexible. A monolithic structure where all functions are tightly intertwined will eventually slow development to a halt. Basic layered architectures can suffer from tight coupling. If the data logic and the user interface are not separated, a small change in one can cause an unexpected failure in the other. The Model View Controller, or MVC pattern, addresses this by separating presentation and interaction from the data handling logic. In the MVC relationship, the model contains processing logic, while the view handles the interface. The controller coordinates, managing view requests to trigger model behavior. The view then reads the updated data. This separation lets engineers update the interface without risking data logic. Isolating these concerns is necessary for building maintainable web and mobile applications that can evolve over time. When an application scales to an enterprise level, even a well-structured MVC system may become too complex for a single team to manage effectively. To handle this, engineers use patterns like the repository to abstract data access. This separates the core business logic from the specific details of the database implementation. The repository acts as an intermediary, ensuring that changes to the database layer do not require the entire application's core logic to be rewritten. For the highest levels of scale, developers move towards a microservices architecture. This approach breaks a single monolithic application into dozens of small, independent services. Each service performs a single function and can be deployed or updated on its own. This creates ultimate technical agility. One team updates the payment service while another scales search, allowing the system to evolve without a total shutdown. Modern software development manages complexity by aligning technical requirements with adaptive human processes and decoupled architectural patterns.